Hello everyone. This video is for folks who missed class on the day that we learned about carrying capacity, or anyone who just wants some review. So what we did in class is we took some notes. Those notes are going to help you on our test coming up. So I'm going to probably go fairly quickly through this. So if you're taking notes, just pause whenever you need to catch up. Okay, so this is what we did that week. Let's skip that. This is today's main question. So how do populations grow? How can we predict that growth? And what is limiting to that growth? Why don't populations just grow and grow and grow? So we're going to be using this equation as a tool today. You are not going to need to use this equation later, but we're just going to use it to kind of look at some theories about what would happen. So I'll stop at a few points at which you can try to use this equation if you'd like, but this equation is not crucial. Understanding it is not crucial to this lesson. So what this is about is it's an equation meant to help us predict future population sizes. So P is what we're trying to find out. That's going to be our new population size. P sub 0, this is one thing together here, is our starting population, how big it is. E is something called Euler's constant, always stays the same in this equation. And up in the exponent, we have K times T. K is the growth rate, always as a decimal, and T is the amount of time. You'll see the amount of time in months, in years, it can vary, but as long as the growth rate is in the same units of time that your time is, you don't have to do any adjusting. As long as those match, you can use this equation. So let's try an example. Go ahead and pause this and see if you can figure out what our population would be. This is how you would be setting up your equation, and you get the answer of 3,308 after 12 months. Now let's look at, if we were going to look at 10 years later, we get a much larger number, 156 million rabbits. So you can see it grows pretty quickly. If we were to graph this population growth, think about what pattern, you might be familiar with these patterns, what pattern you might expect to see. It's going to be increasing quickly, and this is an exponential pattern. If you were thinking of quadratic, that's very similar because it increases rapidly, but exponential increases even quicker than quadratic does. So my question for you is, why are we not all drowning in rabbits? That's not what I want. Ah! Oh dear. Try that again. I was trying to mute it. Why are we not all drowning in rabbits? Why does every place not look like this? And every other living thing for that matter. It's because we have things called limiting factors. These are things like not having enough food or water or living space. These are things like predators that prevent a population from just growing and growing and growing. This is a definition you should write down. Within limiting factors, we have two kinds. We have density dependent and density independent. So density dependent limiting factors are going to usually affect the population more when it gets bigger. Imagine some deer. The more deer you get, the more competition for food there may be. And so competition for food is going to be a density dependent limiting factor. Density independent factors are going to affect the population regardless of its size. So write down those definitions, and then let's make a T-chart. We're going to categorize some different limiting factors into density dependent and independent. So go ahead and pause the video here and put each one of these things into your table where you think it would go. And here are the answers to check your work. Now, there are a few of these that you could make an argument might belong in some circumstances, at least in a different category. So as long as you can explain your reasoning for these two, that's the most important thing. For example, forest fires, if we're talking about the population of trees, becomes a density dependent limiting factor, because the closer together the trees are, the more likely forest fires may be. So as long as you can explain why, that's the most important thing. But notice a lot of natural disaster type things are in the density independent limiting factors, because those things are going to kill organisms regardless of how many of them there are. Disease is a good one. Think about why disease would be density dependent. It has to do with the more packed together, the more crowded a population is, the easier many diseases can spread. So this only counts for diseases that are contagious. But it's no coincidence New York had one of our first major outbreaks of COVID, right? Because it's a density dependent limiting factor. It's going to spread more easily when we have a lot of people in one space. So the truth is, in reality, a population does not usually grow exponentially forever because of these limiting factors. And there's kind of two main options that can happen. This first tends to happen more with things that reproduce really quickly, like bacteria, for example, typically do this. They grow, reproduce quickly, and then they grow too quickly and crash. Another option is that things will kind of level out at a level that can be supported by the environment and all the limiting factors. So it's labeled here K. K is what we call the carrying capacity. It's the largest population an environment can sustain, and that word sustain is very important. Often things will go past carrying capacity. So if it goes up past carrying capacity and comes back down, that wasn't the carrying capacity. Carrying capacity has to be able to be sustained for an amount of time. So here, if we look back at this second graph here, it went past carrying capacity, but where K is, that's kind of where it levels out and can be sustained. So you could look at this, and you could see that where it levels out, I would say around day 23 or so is where they've reached carrying capacity. You also could say the carrying capacity of this species is around 2,000 individuals. So it's interesting to think about carrying capacity when it comes to humans on our planet, because we have a rapidly growing population on Earth, and thinking about where we might level off, or hopefully we won't be like that first J curve where we then crash. There's a lot of people thinking about this, and back in the 70s, there was a big freak out when we first started seeing population growth on our planet really looking exponential. The predictions for 2020 were much, much higher than they are. And it's been an interesting developing field. So just notice that on different continents, we have different growth rates. In different countries, we have different growth rates. Within those countries, in different groups, we have different growth rates. So it varies a lot, and there's a lot of different factors. So I want you to pause right now and take a wild guess. Right now, we have 7.8 billion people on our planet in 2020. What do you think it will be in 80 years in 2100? Just take a guess. So we're going to look at the answer to this in a few different ways. First, let's use our equation to see what it would predict. So the current population is 7.8 billion. We have our growth rate. We're predicting for the year 2100. And by the way, you can do a little cheat here and just make your units be billion. Put in 7.8 as your population, and then your answer will also be in billions. Pause and try that. Here's how I set it up. And here's our answer. 17.3 billion is what our equation would predict. However, what might change before then? Our growth rate is actually already taking into account limiting factors. But there's something about this equation that might change, and that is the growth rate itself. If you think about reasons that people have for having lots of children, we tend to have developing countries have much higher growth rates. There's lots of reasons for that. For example, access to birth control. That could be for cultural reasons. That could be that it simply isn't available near you. That could be cost related. Also things like if you have a high infant mortality rate or childhood mortality rate, if a lot of your children are not surviving, you tend to have more children. You also, if you don't have access to things like a bank account or a savings plan or Medicare, like supports people after they stop working in the United States, you may need your children to help support you as well. So there's lots of reasons that as life gets a little more stable and predictable, birth rates tend to go down. So I feel like often people see these equations and start thinking, oh, well, we have to let disease do its thing and famine and all of these things need to kill people. But if we can actually help people survive more, growth rate goes down and solves that problem as well. So there's a much more humane way to think about these things. Okay, so we made a prediction for population in 2100. We're going to watch this video, and they are going to also explain, listen for the United Nations prediction of our global population in 2100. And the United Nations has a history of making these predictions and being surprisingly accurate. So they base it on many things, and it's a good prediction. And I realized, I just realized that you won't be able to hear the audio on this if I put it in this video. So instead, I'm going to attach this video on this assignment. So this will be the last thing you need to do, is just go watch this video. And then that is it from this lesson. You should be able to explain what carrying capacity is, identify it on a graph or in a set of data. You should be able to categorize density dependent and independent limiting factors, and discuss how carrying capacity applies to global human population.